So I don't think, is there anything else logistically that anybody has questions about? I guess we're just kind of in it, right? You had problem set due last night. Got another one due Friday, which I think does go into, I think there's integration by parts, like I'm trying to get you to remind yourself of just some basic integration by parts. We're not going to do like super hard integrals in this class because we don't teach integration techniques so much in this class, but just to remind you what integration by parts is, and then I think there's stuff on numerical integration, like the midpoint trapezoid stuff that we were doing. So that's the Friday homework. Okay. Today I wanted to get into improper integrals. And you guys watched videos, you took notes. I guess, so I can kind of give a general overview, but also, you know, I always want to have like a Q&A part of like, from the videos you watched, what questions did you have? You should think about that when you're watching the videos, like, oh, this was kind of confusing, maybe you can elaborate on it in class, or this made no sense, or I have this natural follow-up question that you didn't address, or so maybe let me say a couple of generalities about improper integrals. I think the videos too, a lot of times I try to tell it like a story, like here's the thing to think about, and then like, oh, look, you know, like what if we keep integrating? What if we integrate from 1 to 1,000 and then 1 to 1,000,000 and then 1 to 1,000,000,000, you know, and then what happens? And then I think the video you watched for today, it was like that. And but the function was always above the x-axis, so it should have been a positive area. Yeah, okay, so let me just say generalities. So improper integrals, and then we can talk about if you have questions or some further examples, and then a more general, I'm gonna talk about some general stuff that's worth working through. I'm not sure why I have the screen. Let's put the screen back up. Okay. So I'll just say something in general. An integral is called improper if it involves infinity somehow. It's kind of the way I think about it. Somehow. Either the interval is infinite, either the interval goes all the way out to infinity. So either the interval of integration is, I guess I should say that this is really always going to be a definite integral, because it's always about, you know, an indefinite integral is really just an antiderivative, and so there's nothing improper. You can either find an antiderivative or you can't. So either the interval of integration has an endpoint at infinity. It could have both. We could also, I'm going to do an example from minus infinity to infinity at infinity, or the function blows up somewhere is kind of how I described it, right? Or the function has a vertical asymptote, or just a vertical asymptote somewhere, or some sort of bad point. Vertical asymptote somewhere within the interval. I mean, if it has a vertical asymptote but it's outside the interval you're integrating over, then you don't care, right? It's within the interval. Okay, so I mean, you could sort of say like horizontal asymptote or vertical asymptote if you wanted, but that's just the kind of what I think of when I think of improper integrals. How were the videos? What questions? Like, we had some examples. Yeah. Okay, great. Yeah. So converging, well, I have to say different from what I said in the video, and I'm not sure I remember exactly what I said in the video, but converging just basically means that there's an actual finite area. Is that what I said in the video, or do you want to be different from that? Sure. Yeah, so convergence, so an improper integral converges, and we're going to do a bunch of examples, and so that'll also hopefully help. It converges if it represents a finite area, right? And a definite integral always represents an area. So it represents a finite area. It diverges if it represents an infinite area. That's the kind of basic sense, but the words converge and diverge are more broad, and it's usually about well, I'll say this, I'll write this down too, but just in words. Sorry, I'll finish writing this first, and then I'll say words. So the other thing that diverge and converge have to do with is whether a limit exists or not. So we say something converges if a limit exists, meaning it like we get something finite. But if we don't get something finite, then if we're taking a limit and we don't get something, either we get oscillatory behavior. Yeah, maybe it's worth. This is good. This is good. Maybe it's worth just kind of more generally. Because an improper integral is a limit, right? It's a limit of like proper integrals. It's always going to be a limit of like actual finite integrals. And so we're going to be taking a limit. Every time I calculated one in one of those videos, there was always a limit I took at some point. Is that right? And that's kind of how you should do those problems, is write it down as a limit. So let me just think about some examples. Like, if we have something like the limit as x goes to infinity of, what's a good example? I don't know. 2x plus 1 over x, something like this. Then this actually gets closer and closer to 2 as x gets larger and larger, because the plus 1 matters less. I mean, you could break it up as 2 plus 1 over x, right? So this equals 2. But if you have something like the limit as x goes to infinity of, x cubed, that's infinity. And if you have something like the limit as x goes to infinity of sine x, this is even another one, like, what is this? Like sine just oscillates back and forth forever. So this does not exist. You can say this doesn't exist also, but it's sort of helpful sometimes to say something a little more specific, which is that it's going to plus infinity or minus infinity. And in these two cases, this we would call a convergence. And these two we would say diverge. The limit converges. Because we're going to see this a lot in this class. So I might as well give you the slightly larger context of what convergence and divergence means. It always comes down to taking a limit. And if that limit exists, we say that whatever we're looking at converges. And if the limit doesn't exist, we say, if the limit goes to infinity or doesn't exist, we say it diverges. Whatever we're looking at. Okay. Is that helpful? Yeah. So, we had if we have the limit, if we have an integral from a to infinity of f of x dx, that is by definition the limit as b goes to infinity of the integral from a to b of f of x dx. Right, so there is a limit involved in the definition. And so if that limit exists, then we say it converges. If it exists, it's a finite number. So if the limit exists as a finite number, then the integral converges. So that's kind of the language we use. Okay. Good. Other questions? I mean, I can jump into some more examples and stuff, but are there other questions from your video watching or like things you want me to elaborate on more? Yeah. Yeah, we will definitely. I'm going to do that. I actually even have a video where I go through the general argument, but I actually just thought it'd be better to do together as a class because it's kind of subtle. But yeah, there's this, basically there's this 1 over x to the p style function, right? Like, and that's the thing we've said, like, so far we've seen, that the integral from 1 to infinity of 1 over x squared converges, right? Because that ended up being finite. But then I think I did also the integral from 1 to infinity of 1 over root x. And that diverges. And I guess the other, I did rewatch at least the first 2 videos this weekend. I was trying to rewatch the 3rd video just before class, but then someone came and talked to me, like a colleague came and talked to me, so I didn't get to finish rewatching it. But I guess I talked about how like the functions die off and go to 0. Like you need that to happen to have any chance of convergence. So for these where the interval is infinite, right? We said to have any chance of convergence for, I guess for this to have any chance of convergence. And this is where things can get subtle and hard to think about because it's a different limit. It has to have any chance of converging. Like it's a necessary condition. We must have the limit as x goes to infinity of just the function itself, not the integral, but the function itself equals 0. And actually, this is something that I think I always find students having trouble with is like, there's always this problem with indefinite pronouns. If you say it goes to 0, you know, like, it's not that the integral goes to 0, it's that the function goes to 0. And so it can like, so some students want to say things like, oh, this converges to 0, but it's like the function converges to 0 as x gets larger and larger. It's getting closer and closer to the x-axis as you go farther and farther away. But the area is not. The area was going to 1. It was getting closer and closer to 1, right? So this actually, maybe I should even say this equals 1, and it converges. But there are limits everywhere. I mean, that's the thing, when you start really getting into calculus, there's limits everywhere, right? We saw Riemann sums, like integrals were limits of Riemann sums. Now we're actually taking limits of integrals, but we can also take limits of functions. And it just gets kind of weird, right? So, and so because of this, because we need the function to go to 0 anyways, you end up with this whole family of functions you can look at, which is basically 1 over x to a power. And that gets at the p thing that Julie was asking about. So let me get into that. So in general, so I guess I can't remember how explicit I said this in the video, but in general, it's good to look at, or it's interesting, at least as a first example, to look at the integral from 1 to infinity of 1 over x to the p dx. They just use p. Almost every book uses p, and they call it the p test when they, because, so this is for any p, I guess we want p to be positive, right? Because otherwise, I mean, p could be negative, but then it's really, that really means the x is up here, not down here. Because the limit as x goes to infinity of 1 over x to the p is 0, right? So that's actually, this is a family, it's a family of improper integrals that all have a chance to converge. And so the question is which, because of this right here. So the question is which do and which don't, right? Because we've seen one that does and one that doesn't. So this, I guess, maybe it's worth writing over here. This is p equals 2, and this is p equals 1/2, right? In those examples. So the question is, how does this work in general? And we can do the full general argument, but I might say that, like, I guess what I want to say is if we start plotting these, remember in the video about convergence and divergence, I actually showed both graphs, and I was trying to really, I mean, one thing that's in the background of all this is I can't stress enough how weird it is that any of these integrals ever converge. You go off to infinity, but you somehow get a finite area. But then the problem is, as soon as you see an example of finite area, you start thinking that, oh, as long as it goes down to the x-axis, it's going to give a finite area. But that's not true because we see this other example where there's not a finite area, right? So like, it all of a sudden becomes a subtle question. When is it finite? When is it not? When does the integral converge? When is it not? And what I'll say is that it's like, let's think about this. So let me draw a picture for you. I was drawing some of these in the video, but I mean, the other thing about 1 over x to the p is it's always going to look like that same shape, right? Like if we have the 1 over x to the p function, it's always going to look something like this, because as long as the exponent's positive, right? It's going to grow, the bottom's going to grow as x gets larger, so the function's going to get smaller and smaller. Yeah.
Just clarifying, if p is less than 1, then it converges, or it diverges later.
That's what the book says, but we haven't seen why yet. Oh, okay. Right. So in that example, it does turn out that 1 is the tip, p equals 1 is kind of the tipping point. And right, 1/2 it diverged, and for p equals 2, the integral converged. Even I have to be careful not to use indefinite pronouns. I'm gonna try not to. Feel free to jump on me if I do. I say it. What's it? What is it? What you can yell at me. So when p is 1/2, the integral diverges. When p is 2, the integral converges. And that was kind of the thing I talked about, is that you have this whole family of functions. Maybe I should try to draw these in different colors. But they all kind of look the same. Like any 1 over x to the p, like if p is really large, actually it'll dive down to the x-axis like that. So these are all like 1 over x to the p, but if p is really small, it may take a while. It's still going to eventually end up at the x-axis, horizontal asymptote, but it might take a while. So this is y equals 1 over x to the p for various p. And down here is larger p are the ones that go down towards, because again, if you're taking the 10th power of the number on the bottom, then the bottom's getting big quickly. So 1 over it's getting small quickly. And so it's jumping down towards getting close to the x-axis quickly. So p larger here, but up here, it's p is smaller. Like p could be 0.001. I mean, maybe it's worth plotting like I did in the video. Maybe it's actually worth, showing you an example. Sorry, I'm pulling up the. Let's try this. I don't know how. Oh, I had that open in a different. Wait, this video is going to come on and actually let me share screen on this. Yeah. Oh, okay. So looks kind of crazy, but I did kind of extreme examples of p-values. So we did 1 over x squared and 1 over x to the 1/2. Those kind of both look the same shape, just one. They were more gently going down, right? But here I put a really high power of p, and look, it dives down towards the x-axis. The function dives down towards the x-axis. As soon as x gets bigger than 1, you're taking numbers bigger than 1 to the 50th power. So you're making the bottom really big. And so it dives down. So there's almost no area down here. So so in that sense, maybe it's not surprising that you end up with a finite area, right? Because it just gets so close to the x-axis so quickly. But if I do x to the 0.01, remember x to the 0 is 1. So that's almost like a horizontal line, but it's not quite. It does grow. This will grow over time. But it grows very slowly, which means 1 over it goes down very slowly. And there's just so much more area under here. And it turns out to be an infinite area, right? I could put in, 1 over x squared and 1 over x to the 1/2 that I had in the video. Let's see if we'll graph all of these. Yeah, so the yellow and the green are the ones that are more gentle because they're just, and I could even put 1 over x. Why not? Oh, I didn't like my 5th one. It only wanted 4. It won't graph 5. Anyways, 1 over x is even between. 1 over x would be like between the green and the yellow, if you believe that. So, okay, so the point is yeah, p larger, p smaller. So it's plausible, since we know, I guess I'm just trying to build like a chain of logic here. Since we know that it converges for some p value, p equals 2. Since we know it converges for p equals 2, I claim we actually kind of know it's going to converge for all p greater than 2, because greater than 2 is going to be going down to the axis even more quickly, so it's going to be a smaller area. But we'll give a justification, but just kind of so it's plausible. So it's plausible, let me just say, plausible based on the pictures and the 2 examples we did actually do explicitly, that the integral converges for large p, and it diverges for small p, for small values of p. But then the question is, where's the tipping point? Where does it tip from converging to diverging? And so what's interesting to do is, well, if you looked at the book, Julia's saying there's already an answer. But it's also interesting to compare. So let's do 2 more examples, and maybe I'll have you guys just kind of do these at your chairs, and talk to the people around you for a few minutes. What if you do the integral from 1 to infinity of just 1 over x? So that's p equals 1. And also do p equals 1.01. So the integral from 1 to infinity of 1 over x to the 1.01. So try to do both of these integrals. Again, it should be a limit. By definition, it's a limit as the right endpoint goes to infinity. So you get a proper integral you can actually integrate. But it's interesting because these are very close to each other. 1 and 1.01 are very close to each other. But I claim you'll get something interesting happening here. Does that make sense? So take a couple minutes and try to do these integrals and, say hi to the person next to you. Hi. Try to work it out. I'll just write the first step for you. You're evaluating these integrals. Yeah, you have to calculate this definite integral, which is a proper integral with the b, and then let the b go to infinity. That's what we were doing, right? So try to work those out. Oh, sorry, let me share again. So take a couple of minutes and try to do that. Compare with your neighbors. Oh, I'm out of coffee. Disaster. What you can do is you can just evaluate, this thing and this thing, just purely as if it was a normal integral, just with the letter b, and then take the limit as b goes to infinity after you've done that. I hear some ln's, which is good. Natural log. Yes. Good.
Isn't that 0? Like ln1. Okay.
We did that. We did that in class the other day.
Yeah.
Yeah, it's true that it's not a natural log of absolute value of x, but all the x's you're looking at are positive, so it doesn't really matter. But it's a good point. gonna walk around and be hover over people and look, make them uncomfortable. Sorry, I'm hovering too close to you.
Yeah, exactly. Oh, like that's just negative 100 over infinity, right? And then the person would be like a second. Why? Maybe it's
I like it.
So it's like a.
Going back here. Sorry.
Do up to this, 'cause that doesn't equate to 0 like up there, so you can't have it.
When you integrate 1 over x to the 1.0, oh, so the 1.01 is in the exponent, actually, not in the,
Oh, sorry.
yeah, so that's actually, you're just gonna use the power rule for that one. It goes like that. It does grow, yeah, so that's the thing, natural log goes to infinity, but slowly, right? So this actually is plus infinity. There are these equations I like to write. There's these kind of equations I like to write. So you have to like think about, and they're all kind of related to these problems, right? So 1 over big is small, 1 over small is big. But even like big to the 0.01 power, if I have a huge number at the 0.01 power, it seems like it might be small or something. But someone tell me a big number. Reasonably big, not like stupid big.
500.
That's very small.
Oh.
Someone tell me a big number. 10 to the 6, that's not that big. Yeah. 1 million to the million? Okay, so that's actually 10 to the 6 to the millionth, which is 10 to the 6 million. 1 million to the million. So 1 million, that's, that's getting big. It's reasonably big. That's the same thing as 10 to the 6th to the millionth power. So that's 10 to the 6 million. So that's 1 followed by 6 million zeros. Pretty big, right? It would take you a long time to write that number down if you wrote out all the digits. What if I take this? So that's a big number. If I take this to the 0.01 power, 10 to the 6 million to the 0.01 power is what? It's 10 to what power? You know. What do you do with the powers? Right, so what's 6 million times 0.01? 60,000, so that's 10 to the 60,000. That's still pretty big, right? So that's why I say like big to the 0.01 is still big. It's not as big. So this is all supposed to sort of like justify this. What about natural log of big? So like, I was talking to Evan here, like, do you believe natural log goes to infinity as the input goes to infinity? You know, if you look at the graph, it really looks like it levels off quickly, but does it? It doesn't have a horizontal asymptote, I don't think. If we just graph the natural log of x, well, even that's, it almost looks like it has a horizontal asymptote, right? But it doesn't. It actually does keep growing without bound. How can you convince yourself of that? Like, what is natural log of like 10 to the 6 million? What's that? I'm just trying to like, when we take these limits, we always have to take these limits when we do these integrals. And then it's a matter of like trying to think about, you have to kind of get these kind of ideas in your head, right? Like even having a 0.01 power doesn't really turn a big number into a small number or anything. It just makes it a little less big. And so, yeah, and then like here, ln of 10 to the 6 million. What's the log rule that we can use? You guys remember your log rules? Yeah, we can bring the exponent in front, right? That's the same thing as 6 million times the natural log of 10, which by the way, from that lab we did, is like 2.3. So it's approximately 6 million times 2.3, which is something, 12 million, something 13.8 million. So that's about, yeah. 13.8 million maybe. Okay, so that's still pretty big. It's not as big. It's definitely smaller. Like here, taking the 0.01 power only took 10 to the 6 million down to 10 to the 60,000, which is a lot smaller than 10 to the 6 million, but it's still really, really huge. Here, taking natural log took 10 to the 6 million down to just a number that's like a very reasonably sized number. That's why I scoffed at your 500. It's all relative, right? We're all the numbers I'm running down are a drop in the bucket. We're like if the ocean of infinity is in front of us, we're still like right against the shore, no matter how big numbers we write down. So, but yeah, so it's smaller, but it's still, you can make it as big as you want. And you can sort of see that if I make this exponent bigger and bigger, I'm basically gonna make this number bigger and bigger. Right. I mean, ln of 10 to the c is c ln of 10. So, you know, the limit as x goes to infinity of natural log of x, you could think of this as the limit as c goes to infinity of natural log of 10 to the c. There's no reason you couldn't sort of say that, right? Which is the limit as c goes to infinity of I'm sort of belaboring this because this kind of argument's going to come up a lot in this class, and I think it's worth thinking about it as concretely as we can, even if the numbers are 10 to the 6 millionth power, and that's infinity. So natural log about counts the number of digits. Log base 10 really counts the number of digits of a number, plus or minus 1. And so making a number big eventually makes its number of digits big. Okay, so sorry, I've been belaboring this for a while, but now hopefully we can answer these two questions and take these limits. So what did you get? So what did you find for the first one? Did it converge or diverge? How many people think it converged? How many people think it diverged? A lot more. Okay, good. It's democracy, so yeah, you just decide what math says. No, math is not a democracy, but at least the majority rule does work here. Okay, so yeah, so the integral from 1 to infinity 1 over x dx ends up being the limit. So that's the thing, is you think of the right-hand endpoint as some fixed number and then you're sliding it off to infinity, right? That's important that you write the limits here, because this ends up being natural log of, I mean, skipping some steps, this ends up being natural log of b, right? Because natural log of 1 was 0. And so that's infinity. And so it diverges. So the integral diverges. So there's not a finite area underneath 1 over x. But if we do 1 over x to the 1.01, what did you guys find? I guess this is really x to the minus 1.01 power, right? So how many people thought this one converged? How many people thought it diverged? No one thought it diverged? Okay, so what happened? What happens when you integrate this? What happens to the power? Someone we haven't heard from. Be bold. Yeah, Charlie. Yeah. Oh, it ends up being negative 100. Okay, yeah, but I like the fact that you said it's really the powers we're going to care about, and the power you add 1 to, so it's still a negative power. It's x to the minus 0.01. So that's x to the minus 0.01, and you said you put 100 or negative 100? I guess that makes sense. If you differentiate this, these will cancel. Good. And that's from 1 to b. And so that's really minus 100 over x to the 0.01 from 1 to b. I dropped my limit. Bad. There's a limit here for the whole thing. I guess you could drop the limit for a while, just not put an equal sign and say, I'm going to calculate this integral and then take the limit. But okay. And so is this what you guys got? Minus 100 over b to the 0.01 minus negative 100, so plus 100 over 1 to the 0.01. Is that right? Is that what you guys got? And what happens to b to the 0.01? Well, that's the thing where big to the 0.01 is still big. So what happens to this fraction here? Yeah. Goes to 0. The bottom gets big, and the top is fixed. So this goes to 0. And so we just get 100, I guess. And so the integral converges. So we do have a finite area. Okay. So that's weird because we just tweaked the power by a tiny bit. And we still got a finite area. So if I actually was to graph, whoa, I don't know what this stuff is. Can I make that go away? What is this? Something strange is happening. I'm pressing buttons on this monitor. It looks like it's cycling through a bunch of stuff, right? Stop it. I think I press enough of these buttons, something will happen. Oh, okay. Nope, didn't work. I don't know what I did. Oh, and now I have this. How can I get rid of that? I'm having problems here, guys. To the 1.01. If I graph these two, oh my God. Sorry. There's only one graph on the screen. Try to ignore all this stuff up here. Why is there only one graph? Oh, there's not one graph. They're just very, very close to each other. And what's fascinating is that they're indistinguishable at this resolution, and yet one has an infinite area and one has a finite area. If you were to go out far enough, I don't think this is far enough. Wait, I want to zoom just horizontally. I was going to hope to make some actual big numbers here. Okay, so now if we zoom in vertically, do I actually see more of a difference? I just went to 10 to the 7th. Come on, zoom in, please. The tension's unbearable, guys. This is not, it's gonna take a while. Wait, can I zoom in like? Oh, I lose the, damn it. Oh, I lost the axis. We're getting close, starting to peel away. Well, it still doesn't look that different, does it? I do claim if you go far enough, you can see a bigger and bigger gap. I mean, the Y range now is very tiny, but the gap is growing. And I guess what I say is if you went farther and far enough along this, the red would actually get really close to the axis compared to the blue at some point if you went far enough away. Okay, does that make sense? I mean, this shouldn't make sense at all. It's weird. It's like quantum mechanics. It's like something that just doesn't make human sense, but that's because we can't comprehend the quantum foam that's happening in the smallest measures of reality. Here, this is because we can't really comprehend infinity. But the math tells us the red graph has a finite area under it, the blue graph has an infinite area. Okay? And it really does come down to the fact that that here became a natural log, which does go out. This goes to infinity slowly. And here, when we integrated, the x was still in the bottom. I mean, the other example I could have given you to do was the 0.99 power. P equals 0.99, whatever x to the 0.99. And if you just think about if we change these numbers to 0.99, what would happen? Like if that was 0.99, then this would be 0.99. Now, what would happen when you integrate minus 0.99? What would this power be? Plus 0.01, right? Because you add 1. And all of a sudden, this x would move up here. And this b would be up here. And now the top would get large. Sorry, the constant probably changes too. Maybe somehow, I'm just trying to show you just in general sense. And so now it would actually blow up. So it's the reason the tipping point here is at 1 is because the -1 power is sort of the weird tipping point for the power rule, for the antiderivative power rule. Where if you're less than -1 and you integrate, you're still at a negative power. But if you're greater than -1 and you integrate, you're at a positive power. That's kind of what's happening underneath here, I think. But I can state the general rule now. And I think I go through it fully generally in another video on my playlist. Like and subscribe of my videos. Oh wait, I've heard another one. Like, subscribe, and hit the notification bell. That's another one I saw recently. Guys, I'm really just a content creator. My niece and nephew loved this YouTube channel called Blippi, something. Do you know what I'm talking about? this guy who just kind of like, hey kids, and like shows them stuff. And we found out the guy makes like 20 million a year just by having this YouTube channel and like merchandises. I was like, damn, went the wrong business. Could I make a math YouTube channel that made me 20 million a year? Probably not. Thank you. I should do it. That's right. You can, yeah, you'll say like, we knew him when. And I will retire. You could be my first subscribers and my last students. Anyways, okay. So what was it? What was I talking about? Oh, so the general, that's sort of the quote unquote P test. We're going to see a couple different ones of these, but the integral from 1 to infinity of 1 over x to the p dx, there's two things. It converges if p is greater than 1, strictly greater than 1, because we saw that from 1.01. And it diverges if p is less than or equal to 1. Okay. So that's the general statement of what we just did. I mean, I could have done it fully in general with p's instead of numbers, but I just think it's more evocative when you do the numbers, see how things actually grow. Okay. So that's the first, that's kind of like the avatar for a lot of improper integrals, at least when you go to infinity. I will say that there's others. We're done. Do we need a break for a couple minutes? Who wants a break for a couple minutes? You're not going to say no, right? Let's take a break for a couple minutes, come back, and then push through for the last 25 minutes and talk some more. We covered the main. Five-minute classes are just a little. "85 minutes of math teaching gets to be a little much."
It's so weird. Like, I virtually have all the class in high school, but there's probably a lot of kids who have only ever had like 45-minute classes.
Yeah, like college.
3-hour lab set.
Right. And all of a sudden you're like, okay. But yeah, I just feel like, I don't know, I found students do not like an 85-minute straight lecture. I mean, I tried to break it up and have you guys do the problems and stuff, but still, like,
This is interactive, but it's just like a big job or something.
the person just talks. Yeah.
Those drag out.
That's the thing that I was amazed by when I started like having friends in other departments and stuff. Like when you're in grad school, you basically only know people in your area. But then when I came here and I started making friends with other departments, and I would like go to their talks, like in English or history or something, they're almost just reading a paper when they give a talk, and they might have slides. And you do not interrupt, you ask questions at the end. And so a friend of mine was doing a practice talk for something, and I was like, oh, I'll come watch, and I'll like give you feedback. She's like, yeah, please. And 10 minutes in, I'm like, a question, and she's like, what? Because at math talks, like you just interrupt all the time. People interrupt. You just ask a question whenever you have it.
You don't remember your issue an hour later.
Right. And maybe humanities stuff, it's like more philosophical. You want to go in depth to something, you just kind of save it. But in math, it's usually something like with the notation or something weird. And yeah. And so we got in math, the culture is just to ask immediately, which is what you should all be doing. Because if any of you have a question, then I'm sure half the class has the same question. But yeah. You guys are getting PCR tests twice a week? And we're doing, faculty's back to doing once a week. Go back to what? Yeah. It's funny, wait, are you first year, second year? We didn't even have a green status last year.
I know you did it.
Yellow was the best we had.
The senior, I was talking to some of the seniors, they were like, we never went back and we're not anticipating going back this year because like Bowdoin tends to be really like
Conservative, but yeah,
about, so even with like 10 cases, they might stay yellow.
right. I mean, I'm hoping this was all just,
Because it's like, it's one tower that's spread it.
right. And I mean, I'm hoping it was just the transition back to campus and now it'll like settle down and,
Yeah, that'll be like contained. I guess
Yeah.
the difference is that we're all vaccinated now.
yeah, so nobody's really gonna get really sick, but we just don't want to spread it.
And we're getting boosters too.
Getting what?
The booster, there's a girl who got it in.
Oh,
her
the
class.
booster. Oh,
Yeah.
already?
Yeah,
Really?
already.
Oh,
She was in,
yeah.
Like the trial or something.
Oh,
Yeah.
yeah, no, my mom was talking about it last night because we're having like a family funeral gathering in like a month. And that we've been putting off for like a year. And now it's like, are we gonna put it off again or can people get boosters or, you know, so.
You got it as like.
All right, maybe it's been at least 5 minutes, so let's get back to, we've got like 24 minutes left in class. So let's hit, okay. So I want to do a few more examples and I'd like to talk about the other type of improper integral where the blows up at a vertical asymptote instead of a horizontal asymptote. Just as something that's not a 1 over x to the p, you could have like an exponential decaying function. Like here's an example, you could have like the integral from 0 to infinity of e to the minus x dx or something like that. I can't remember if I did an example like this in the video. But if I was to graph, I mean, in fact, let me compare it to like 1 over x. Let me graph e to the minus x. On screen. So right, e to the, so by the way, notice I did the integral from 1 to infinity here because this function's bad at 0. It blows up at 0. We'll actually talk about like the integral from 0 to 1, which is also an improper integral here. But here, e to the negative x is not bad anywhere. So it's like it doesn't blow up. It doesn't, you don't have vertical asymptote anywhere. So you can see, but it turns out this like, because it's exponential, it's really 1 over e to the x. It dives down towards the x-axis again and chokes off a finite area. And you can see this pretty easily that it's like, so again, by definition, it's the limit as b goes to infinity of the integral from 0 to b, e to the minus x. But then that is not a very difficult integral for us, right? What's the antiderivative of e to the minus x? Someone's saying it, I heard someone. Negative e to the negative x. That's right. So negative e to the negative x from 0 to b And that's negative e to the negative b minus negative e to the negative 0. So minus minus made a plus. So that is probably, you can see it now, like you could think of this as -1 over e to the b if you wanted to, the negative power, right? Plus 1. And now that's getting really big. Should have another like e to the little big is big, big. How the bigs work in that case. So that goes to 0. And so it's just 1. And it converges. So that's another example. Oh, something I meant to say. I integrated from 1 to infinity here, but it actually doesn't really matter where I start. All the question of convergence and divergence happens in that limit. So like, just as a second, I mean, I'll just put this number 2. The integral from like 7 to infinity of 1 over x to the p, or the integral of 0.01 to infinity of 1 over x to the p, those behave just exactly like the integral from 1 to infinity. They don't have the same, if they either converge or they both converge or they both diverge. Like, so the 1 was not special here. I mean, if it converges, it changes the value, certainly. But, right, like, if you had something like, if you have something like this, and you want to think about the area from 1 to infinity versus the area from 7 to infinity. Right, like whether that's finite or infinite has nothing to do with this piece. This piece is definitely finite. So if the whole thing's finite, then the blue is finite and the pink area is finite. But if the whole thing's infinite, then the blue area is infinite and the pink area is also infinite. Yeah.
What if we try to integrate from 0?
Right, if we try to integrate from 0, then we have this other, it's actually improper at 2 places. It's improper at 0 and at infinity. Sometimes we say improper at, like when we talk about the point where it's in point or points where it's improper. And I'm going to do an example like that. You actually have to break it up into like the integral of 0 to 1 plus the integral from 1 to infinity and evaluate each separately. And then if either of those is infinite, then the whole thing's infinite. I'll give some examples there in a second, but yeah. Yeah, like these areas are either both infinite or both finite. So a lot of times you can sort of like, right, I mean, it's a good point. Ahmed is bringing up, because I can't just change this to anything necessarily. At 0, there's this vertical asymptote we have to deal with. But as long as I'm not crossing the vertical asymptote, it's either these either both are finite or both are infinite. So that's worth just noting explicitly. Let me give you another example, a couple more examples, just to show you things can work, how things can work a little bit differently, or I think another example I give you can be controversial. Mathematics can be controversial. It's like, I've had a lot of arguments with people over whether 0.9 repeating equals 1 or not. How many people think 0.9 repeating does equal 1? How many people think 0.9 repeating does not equal 1? Okay, this is definitely not a majority rule because you're all wrong. 0.9 repeating definitely equals 1. And I will argue about it with you at some point, not in class if you want. 100%. Okay. If you are dubious, okay, I'll just say so. 0.3 repeating is 1/3, right? So add 3 copies of this on the left side, what do you get? Add 3 copies of this on the right side, what do you get? Boom! All right, that's one. I can give many other arguments, but it's surprising. I mean, it's surprising. It's weird. It's true though. Okay. Where was I? Oh, examples. Okay. Here's one. Minus infinity to infinity of 1/x² + 1 dx. So I could graph this. If you're watching at home, graph it. This is a pretty nice graph. It's just like a little, hump in the middle and then dies off on the other side. This actually gets at the question earlier, like we really should, this is improper at both endpoints. And so you really should break it up into 2 improper integrals. So I'm going to say this, it's actually the integral from minus infinity to 0 plus the integral from 0 to infinity. And so by definition, this would be the limit as b goes to -infinity of the integral -b to 0. I'm sorry, b, it's really just b. Saying b is a negative number, right? Plus the limit as b goes to +infinity of the integral from 0 to, no, I should use a different letter. Let's say a. You might ask why I'm doing this, and I will, instead of just having the limit of like -b to b, and I will give an example soon. Yeah. You would think that, right? I'm gonna give you an example in a moment that's gonna say that you shouldn't do that. But you might, it also might be controversial, like 0.9 repeating equals 1 is controversial. Like you might disagree with me, but I'll give you an example in a second. So, okay. Here's the thing. Who remembers how to anti-differentiate 1/x² + 1? Let u be the bottom. Problem is the du would have an x in it, and there's no x up here. Yeah. It's a trig substitution thing. Yeah, and it's actually, yes, it is. And it's actually something that you might want to remind yourself of, that the derivative of the inverse tangent function is actually 1/1 + x². And so there is a trig substitution way to do that, but you can, for something simple like this, you can just kind of remember that like that's the derivative. So actually the antiderivative of this is this. I'll plot the inverse tangent function on the graph also. If you don't, you probably don't think about inverse trig functions as much as I do. So you may not remember, but there's this function called arctan or inverse tan that looks like that. It's basically you take the tangent graph and you flip it because it's the inverse function. It's basically the opposite. Like trig functions take angles to numbers, like sine takes an angle to a number between -1 and 1. The inverse trig functions take numbers to angles. You plug in, like for inverse sine, you plug in a number between -1 and 1, and you get out the angle that gives you that sine. Same thing here. You plug in a number between -infinity and infinity, and it spits out the angle the tangent would give you, whose tangent would be that number. And so what happens is, So, okay, so I guess what I'm saying is this is actually inverse tangent. This antidifferent, it's good to have a little bit of a tool book and try to remember some of this stuff. So this is, inverse tan is also called arctan. There's just the same, it's different names for the same thing. From b to 0 plus the limit as a goes to plus infinity of arctan x from 0 to a. So the real question is, what is like arctangent of infinity? Because, this ends up equaling arctan of 0 minus arctan of negative infinity plus arctan of infinity minus arctan of 0. All of a sudden, I've stunned you all into silence with this arctan business. So really, actually, I think Evan had the question, why can't we just do this as 1? We couldn't just do the limit from like negative a to a or something like that. And you see actually the tangent, these cancel, the tangent 0, inverse tangent 0s cancel. So this actually really is inverse tangent of infinity minus inverse tangent of negative infinity, which just looks like absolute nonsense. Except if you follow this graph out to the right, this graph of arctan, it really does seem to have a horizontal asymptote, right? And also this way it has a horizontal asymptote. So the question is, what are those horizontal asymptotes? And this gets a little bit, this is stuff I'm happy to go through more like in a Friday class or an office hours or something. But do you think when you woke up today, you were going to be asked what inverse tangent of infinity is? So how does tangent work? Tangent is opposite over adjacent, right? That's theta. So tan theta is opposite over adjacent. And so actually, like here, I'll give you an example. Tangent of pi over 4, tangent of 45 degrees is 1, because if this is 45 degrees, these are the same length. And so I'm saying when you turn it around, inverse tangent of 1 is pi over 4. You just reverse the function. It's like squaring and square rooting or adding 5 and subtracting 5. You just kind of reverse what you're doing. So the inverse tangent of 1 is pi over 4. So if I did zoom in on that graph and found x equals 1, you would see the y value. I think switch, so I'm actually following. What's pi over 4 approximately? It's 0.78, 0.7879, a reasonable amount for pi over 4. Yeah, okay, so that's actually pi over 4. What happens as this angle gets closer and closer to 90 degrees? What happens to the triangle? Yeah, and the opposite side gets longer too. So what happens to this fraction? It's bigger and bigger and actually goes to infinity. And so at 90 degrees, you actually get infinity. Tangent goes to infinity. If you just graph tangent itself, maybe I should have graphed tangent on here too or something, or maybe another tab. I'll graph tan x. Yeah, it has all of these vertical asymptotes. But but they are actually at pi over 2. And then some sort of multiples of pi over 2. Right? Like pi over 2 is about 1.57. And so between here and here, I've gone past the asymptote. So my point is that you can convince yourself that inverse tangent of infinity is actually pi over 2. Because that's the x value here as y goes to infinity. The x value is pi over 2. And then over here, it's negative pi over 2. So it's minus negative pi over 2. So this is actually pi. So that's the area under 1 over x squared plus 1 from negative infinity to infinity. It's actually a finite area, and it is pi. Okay. Any questions about that? Yeah. Right, actually, so that's what you were asking about too. Like, yeah, so if you have, okay, so that's interesting. And actually, maybe that's the last thing I should say. Yeah, there was another example I was gonna do, maybe just as a example for you to think about before I get to that. Is it's sort of interesting to do this function, which this actually would use a u substitution now. Instead of having 1 over x squared plus 1, you could do x over x squared plus 1. If I plot that, we still have a few minutes. Right, so this actually looks like this. And maybe I'll just say this in words, like, it would be easy to convince yourself that, what would you think the total area under this graph would be? What kind of area is that kind of area? Negative area. And so it would seem that it would be negative area, positive area, and there's a symmetry that would cancel out and be 0. But that's where the controversy is that if I integrate this from 0 to infinity, it turns out it diverges. So maybe I'll just say this, like, looks like 0. And if you did it, you could see. But the integral from 0 to infinity, x over x squared plus 1, you can actually see that it involves a natural, like you can do u equals x squared plus 1, and you can convince yourself it's basically a natural log is involved, so it does go to infinity. But this diverges. So that area of the positive area here off to infinity is actually an infinite area. And so we don't really want to say this area is 0 because you're missing the fact that there's an infinity in there somewhere. But there's some convention to that, like whether it's sort of yes or no. But I guess what I'm saying is, so we say that this whole thing diverges. Because if any piece of an integral diverges, the whole thing should diverge. We don't want to call something finite if it's like canceling infinities or something. I mean, I guess I'm saying that this is kind of controversial, and I can argue with students about this, but we don't have much time today, so maybe I'll argue about it with you on Friday or something. Okay, so then the very last thing I'll say is there's a different p-test. And the video I had you watch for today, I think I did the integral of 1 over x squared from like 0 to 1. Did I do that in the video for today? You guys forgot already. And it actually flips. It turns out that the integral, so let's just say from the video, we now look at, and I'll have to do this more on Monday, but this one actually diverges. If you let the limit go to 0 down here, you can see this diverges. But if you do the 1/2 power, it actually converges. So it actually ends up being like this, but almost flipped. The stuff that converged for 1 to infinity diverges from 0 to 1. And so there's a p-test for this too, which is at the integral from 0 to 1. It converges if p is less than 1, and it diverges if p is greater than or equal to 1. So actually at 1, it still diverges, both diverge. But otherwise they kind of flip. And as the very last thing I'll say, that means that if you do the integral from 0 to infinity of one of these functions, it never converges. Because either this piece diverges or that piece diverges. Because there's no value of p for which they both converge. And so it's a little bit frustrating, but like, if you wanted to look at the whole area under 1 over x squared, for example, like the area from 1 to infinity is finite, but the area from 0 to 1 is infinite. And so that's just kind of just like a curiosity that you can never get a value where it always converges. Okay, let's stop there because we're out of time. And Friday, again, will just be like glorified office hours. Come talk if you have questions about the homework. And then there's a video on comparisons of improper integrals from Monday. So we'll finish up improper integral stuff and go to comparisons of improper integrals on Monday. And you can email me for office hours, stuff like that. Thanks, everyone. Yeah. You too.